Roberta Angius from the University of Hamburg, telling us about thimble decomposition and wall-crossing structure for physical integrals.
Okay, hello again to everyone. Thank you for the introduction, and thank you to all the organizers for the invitation. It is a very pleasure for me to be here to present this work. So, as you can read from the title, in this presentation, I will talk about thimble decomposition and wall-crossing structure for physical integrals, a project that I carried out in super great collaboration with Sergio Cacciatori and Unima Sita, both in the audience. So, the main motivation for this research came from the fact that the analysis of physical systems across different domains often require the evaluation of very complex integrals. And solving these integrals typically demand very powerful computational techniques. Sorry, I will change my place.
It's good.
Okay. But solving this integral typically demands very powerful computational techniques to directly attack the integral or to solve complicated system of differential equations for which the integral is a solution. However, these two methods can be exactly implemented only in very few cases, and most often the integrals are treated perturbatively. So, an alternative approach to address the same problem could be the one to exploit our geometric interpretation behind the integral to try to simplify it using techniques coming from algebraic geometry. So, before we go on, let me explain what I mean with geometric interpretation behind the integral. And here, the idea is the one to look at the integral itself as a period in the sense of Kontsevich-Zeiger, namely as a complex number obtained by integrating a certain differential form over an algebraic or semi-algebraic subset of a complex algebraic variety. Then, this means that our integral defines a period if it can be interpreted as a non-degenerate pairing between a certain cohomology group containing the integration form and a certain homology group containing the integration contour. And in this language, the whole information about the geometry behind the integral is fully encoded in this algebraic variety and on the shape of some of its internal cycles. We will see later which cycles. So the integration contour is a subset of this variety. The integration variables are coordinates for this variety. And these eventually extra parameters here that I'm calling mu1, mu2, etc., can be interpreted as moduli for this variety, controlling the size and the shape of some of its internal cycles. So the question could be, which are the advantages to use this period interpretation? And of course, the main advantage is that now the value of the integral only depend on the homology class of the integration cycles and the cohomology class of the integration form, but it doesn't depend on the specific representatives. Moreover, both the homology and the cohomology rings are finitely generated. This means that we can associate to both of them a basis with a finite number of elements. Here I'm using the notation gamma 1, gamma n to indicate the basis for my homology group, and omega 1, omega 2, omega n to indicate the basis for my cohomology group. Again, we can define inside these two bases a non-degenerate internal product that in the case of homology is nothing else than topological intersection among cycles, and in the case of cohomology is the corresponding Poincare dual product. In the picture, I just represented the first singular homology group of this Riemann surface X, and I indicated with the green dots, in green, okay, the topological intersection among the cycles that I choose to define my basis. Now, using these two properties, I can interpret my initial integral as an element of a finite dimensional vector space spanned by master integral and equipped with a double projection. This double projection gives us two different ways to define master integrals. The first possibility is the one to fix a basis and an internal product inside my homology group, such that I can decompose my integration contour here in terms of my basis, and using linearity of the integral, write the integral in terms of this linear combination of master integrals, which are defined integrating the differential form omega over the different cycles of the basis. The coefficients in this expansion are nothing else intersection numbers in homology. A second possibility is the one to fix a basis and an internal product in my cohomology group, such that I can decompose my integration form in terms of this basis, and using linearity, write this second decomposition for my initial integral. In this second case, master integrals are defined keeping fixed the integration contour and changing the integration form over the basis of the cohomology. In this case, the coefficients are intersection numbers in cohomology. In general, people in physics use this second decomposition in terms of cohomology, but in this talk, I will mainly use the first approach in terms of cycles. Of course, the two procedures should be dual. Okay, so far the idea seems very nice. However, when we try to apply it to certain specific physical setups, we immediately hit several problems. And to underline some of these problems, let me take a concrete example. And let me consider Feynman integrals in Bykov representation, in which we have an integral over an open contour of this Bykov polynomial on the variable x, depending on a bunch of parameters mu. These parameters define kinematic quantities like the masses or the external momenta of my particle involved in a certain interaction. And this polynomial is raised to this power minus gamma, where gamma is in general not an integer number. And finally, I have this rational differential form omega. Now, the main problems here arise due to the fact that the exponent gamma is not an integer number. This leads to multivalued integrals with a potentially complicated monodromy that kill my geometric intuition about what a manifold X could be. Again, for special values of the parameters mu inside the Bykov polynomial, I can have a singular manifold X that impose further complication, let's say. So these issues make difficult in many situations to identify the right homology and cohomology group to define the pairing. Let me point out that this, of course, this idea of exploit the period interpretation in Feynman integral and use intersection theory to perform the master integral decomposition is something not new in physics. I just want to underline two references. There are many of them. We had a lecture by Julio, but I want to point out this reference of FAM in the 80s and this reference by Mastrolia Misera in 2018. Okay, in the meantime, many computational algorithms have been developed to perform this master integral decomposition using these intersection theory methods. However, many cases, as for example, limits of singular varieties, are still a problem. So the plan of the presentation is the following. I will start proposing a solution to the problem for many physical setups, which is given by exponential integrals. Then I will study the wall-crossing structure of families of exponential integrals. Then I will discuss exponential integrals defined through holomorphic and multivalued functions, and I will conclude with some final remarks. Okay, so the solution, the general solution for many cases of physical interest has been proposed has been described in full generality in this paper by Kontsevich and Soibelman, and the solution is given by exponential integrals that define a non-degenerate pairing between the Rham cohomology and this so-called Betti homology. So the key ingredients that we need to define this pairing are the following. First, we need to know an n-dimensional complex algebraic variety X. Then we need a complex valued function f over the variety, which is the one that appears here in the exponential. We need an holomorphic volume form over the variety and an n-dimensional open integration chain on the variety, except support on the variety except a possible non-empty subset D0, and such that the restriction of the real part of f over the support of gamma define a proper map bounded from below. This last condition is necessary to assure convergence. Actually, in my talk, I will use a generalization of these exponential integrals obtained just by rescaling the function f by a complex number gamma. This generalization gives me a whole family of exponential integrals depending on this parameter gamma that appear here then in the exponential. In particular, you can notice that both the cohomologies involved in this pairing depend by the value of gamma. In particular, by varying gamma, these cohomology groups can change, and for special values of gamma, they can even reduce the exponentiality, leading to a reduced number of master integrals. Then, to study how the structure of this pairing change for different value of gamma, correspond to study the wall-crossing structure for my family of integrals. I will discuss this wall-crossing structure more in detail later, but before to do this, let me introduce briefly the two objects that define this pairing. Okay, on the first side, we have this the Rham cohomology, which contain equivalence classes of closed form with respect to this twisted differential, and support on the manifold X except this possible non-empty divisor D0. Notice that so far the twist that I use to define this twisted differential is this one form alpha defined in terms of the function f. Then this alpha for the moment is an exact form. Okay, this function f was the one appearing in the exponential in the integral. Actually, I can define a generalized version of this cohomology, just taking into account of the value of gamma in the definition of the differential, of the twisted differential. Now, the other object involved in the pairing is this Betti homology, which captures the topology of chain on X relative to the level set of the function f at infinity. This means that the integration cycle gamma that live in this homology group is a non-compact n-dimensional cycle on the variety X with boundaries on this set. This set is the subset of X at which the function f diverges. Now, even in this case, I can define a generalized version of this homology, just taking into account of the value of gamma when I compute the preimage of f. This means that I can consider the whole gamma plane and associate to each point of this plane the corresponding Betti homology, and study how this homology change when I move across this gamma plane correspond to study the wall-crossing structure of my family of integrals. Now, let me go back to my initial problem, and let me consider a specific integral E having our favorite exponential form. What we want to do concretely is to define a basis of integration contour for the Betti homology group, then define inside this basis an internal product that gives me the intersection numbers among cycles, such that I can decompose my integration contour in terms of this basis and write the master integral decomposition for my former integral. Okay, this is the idea. So let's start with the first point. Define a basis for the Betti homology group. Okay, so far I introduced two kinds of cohomology associated with the pair XF. where x is a complex algebraic variety and f is a complex valued function over the variety. Actually, I can introduce at least two other cohomologies associated with the same pair, but that can be constructed only using local data. They are the so-called Rham local cohomology and this local Betti homology. Let me focus in this local Betti homology. And let me assume that the function f has finitely many non-degenerate critical points that here I'm indicated with sigma 1, sigma 2, sigma n, all associated with different critical values that here I'm calling T1, T2, Tn, that form this set S. Now, if we fix gamma and a positive real number epsilon, we can associate to each pair Te gamma, where Te is one of these critical values, the following homology group. Let me explain the ingredients that are in this definition. This D gamma T epsilon here is a closed disk in the T plane centered in gamma T with radius epsilon. Here I'm considering gamma equal to 1 for simplicity. And this T theta gamma is a point in the boundary of the disk located along the direction theta, where theta is given by the argument of gamma. Then, when I'm computing this preimage, I'm computing the preimage of this disk and this point on my variety X, essentially. And this is nothing else, a sort of local relative homology around my critical point. I can define an homology like this for any critical point in the set S. Now, summing over all these local relative homologies, I obtain what I call the local Betti homology. Now, the important thing is that there exists a local to global isomorphism that link my local Betti homology to its global version. The most relevant consequence of this is that I can reconstruct my global Betti homology only using local data. The procedure requires different steps. Let me start with the first step. The first step requires to consider the level sets associated with the function f, which are given by this kind of equation for different values of t. Now, for different values of t, this equation defines an n-1 dimensional complex algebraic variety because I have n coordinates. This zeta is a vector, I have n different zeta. Now I can represent this whole family of varieties just fibering the t-plane and associate to each point of this plane the variety defined by the corresponding algebraic equation. Now, from a geometric perspective, when I move across this t-plane, what I'm doing, I just change the sides of some of the n-1 dimensional internal cycle of my variety. This is the first step. Now, the second step consists to define the set of critical points for my function f and compute all the critical values. Now, from a geometric point of view, in correspondence of the critical value, the variety in the fiber becomes singular. This means that as I approach each of these points, some of the n-1 dimensional internal cycles shrink to 0 sides. And for this reason, I'm calling it a vanishing cycle. And then I can associate to each critical point in my t-plane a specific vanishing cycle that here I'm calling delta I. Now, the last step consists to construct thimbles. To do this, I can consider the direction theta given by the argument of gamma in the t-plane, and starting from any critical point, draw the trace of the vanishing cycle along the direction theta. Okay, these manifolds, this blue and these pink manifolds, are constructed drawing the trace of the vanishing cycle along the direction theta. The direction theta is given by gamma. Okay. These resulting manifolds are what I'm calling thimbles, and they have the right dimension n to be integration cycles of my initial integral. In fact, this whole set of thimbles constructed along the direction gamma form a basis for the corresponding Betti homology group. Then with this geometric construction, I construct a basis for my homology. Then I can go to the second step. Define a non-degenerate pairing inside this basis. Now, for generic values of theta, thimbles associate to different critical values never intersect, of course, no? But I can define an intersection pairing between the Betti homology group written with respect to its basis of thimble and this dual homology that I obtain just by shifting the argument of gamma by pi. I can define a basis of thimbles for this dual homology just drawing the trace of the vanishing cycles in the opposite direction. Essentially, this is the critical point E. This green one is the thimble associated to the standard Betti homology. If I draw the trace of the vanishing cycle in the opposite direction, this is a thimble that it is in the basis of this dual homology. And with respect to these two bases of thimbles, the intersection product is just given by this delta, which means that only thimbles associated with the same critical values intersect and intersect only once at the critical value. Okay, then I have a basis, I have an intersection product, then I can think that I can perform my master integral decomposition for any value of gamma. But this is not true, because for special values of gamma, some new phenomena can emerge. And problems emerge for values of gamma for which the line, the direction theta in the t-plane intersect two or more critical points. Okay, I call such a direction in the t-plane a Stokes line, and I call the corresponding direction in the gamma plane a Stokes ray. What happens is that when I have a direction like this, the thimbles associated with the critical points T1 and T2 degenerate one into the other. Then this reduces my total number of thimbles and lead to a wrong computation maybe to the number of master integrals. That's a problem. Then for a given family of exponential integrals, I can have different Stokes rays that split the gamma plane in different sectors. And to study how my basis of thimbles equipped with an intersection product change as I move across these different sectors, correspond to study my wall crossing structure. So let me explain what happened. Let's suppose that I want to cross this ray, going from region 0 to region 1, and such that this Stokes ray in the gamma plane correspond to a Stokes line in the t-plane that connect the critical values TE and TJ. What happened is that the corresponding thimbles, that here I'm calling gamma E and gamma J, undergo a discontinuity jump described in terms of a matrix like this. This matrix map the two thimbles, gamma E, gamma J 0, which are defined in this region 0, to these new thimbles, which are defined in this region 1. And the relevant entry in this matrix is this number gamma ij, and this number gamma ij is nothing else the intersection number among the vanishing cycles delta E and delta J that I use to construct my thimbles. Then the relevant point here is that only using local monodromies around the point TE and TJ, I can compute these intersection numbers using Picard-Lifshitz theorem. Now, I can do something more. I can even evaluate my integrals along the thimbles to determine which thimbles are dominant in the different sector in the gamma plane. To do this, I can fix gamma and define this vector valued function in which each entry of this function is my exponential integral evaluated along the thimble. Now, for gamma to infinity, each of these entries admit a power series expansion in gamma having this form. And what I want to do is to compute these coefficients. To do this, I can consider the following change of variables. This new variable s parameterizes the distance from the critical value TE in the T plane, and I can write the corresponding thimble just using the definition. I'm just the union of the vanishing cycles along the direction S. This is just a definition. Now, using the Rham map, I can write my integral in this form. Let me explain what it is, this form. This function, vol of S, is nothing else the volume of the vanishing cycle fiber over the position S. Then essentially, what I'm doing, I'm splitting the integral over the thimble as an integral over the vanishing cycle times an integral over the direction S along which the thimble extends. And I just splitting my integration into parts. Now, the expectation is that the biggest contribution to the integral is given by vanishing cycle close to the critical point, then this pink region here in this picture. And the good point is that the volume of these cycles here close to this point admit close to S equal to 0 a series expansion having this form, which can be completely determined in terms of local monodromies around the point S equal to 0. In particular, this gamma here that appear in my expansion are numbers associated with eigenvalues of the monodromy operator, and this K run from 0 to the dimension of the corresponding Jordan block. Then yes?
Sorry, you're not assuming anymore that you have isolated critical point and isolated critical value.
Yes, I have isolated critical point.
But like not simple. So they can be degenerate, they can have some multiplicity if you have these logs or not.
I can have some multiplicity if I have this log. Why?
I mean, this Jordan block is not
in general, my monodromies, for example, even in the case of the elliptic, no, they correspond to a 2 by 2 blocks, no?
Okay, so you have some of. Okay, fine. I thought
no. I can have logarithmic.
Even if you have non-degenerate critical point. If your function f has non-degenerate critical point.
Yes.
That has a
They have the same critical value.
Okay. That's it. Okay. Okay.
Thank you.
Thanks.
Okay, then I take this expansion for the volume and I put this expansion inside my integral. Then I use gamma function identity and I compute this value. Then I can compare this value with my series here and extract a closed form for my coefficient C, given in terms of derivative of the gamma function. Okay, now in order to understand how this procedure works in a concrete case, let me take the simplest example that I can consider, the case in which the function f is an holomorphic function. In this case, the previous analysis matched with the study of Lie thimbles in Morse theory. In this case, my variety x is just given by Cn. I can define my Morse function as the real part of gamma f, and the thimble that I construct using a geometric way in the previous slide exactly match with the Lipschitz thimbles, which are solutions of gradient flow equation like this one, where this G is a Riemannian metric over this variety, and these U, E, U, J are real coordinates on the variety. Solutions of this equation always satisfy these three properties. First, the imaginary part of gamma f stay constant along the path that are solutions of this equation. Again, each of these paths pass through a single critical point, and the Morse function is monotonically increasing along this path. These three conditions are necessary to assure convergence. Okay, let me skip this. Let me go directly to this example. In this case, I'm considering this per C integral, describing the grand canonical partition function of a nuclear matter model. Essentially, what I have is that my function f is an holomorphic function in a single variable, and it is a quartic polynomial depending on the parameters b, c, and d. My algebraic variety is c. Then I start computing the critical points for the function f, which are zeros of this cubic equation. Now, the solutions of this cubic equation, of course, depend on the parameters b and c. In particular, I can distinguish among three different regimes depending on the sign of this delta. In the case delta bigger than 0, I have one real and complex conjugate solution. Delta smaller than 0, I have three different real solutions, and delta equal to 0, I have three real solutions with at least a multiple root. Okay, then I'm essentially splitting the parameter space in A and B in three different regions, three different regimes. Let me start with the first regime, the delta bigger than 0. In this case, I have three distinct critical points. Then I can construct three distinct thimbles for my Betti homology, which are given by these branched paths in this picture. And three thimbles for my dual homology, which are these blue lines in this picture. Now, once I have these for a specific value of gamma, I can start computing my wall crossing structure by varying gamma over the gamma plane. In particular, in this case, I can find three different Stokes lines that split my gamma plane in 6 different regions. Okay, the method that we use to construct the thimbles and to compute this wall crossing structure follow the procedure that I described in this previous slide. Then we start fixing gamma. We have three critical points, and we compute the corresponding critical values. To construct thimbles, we construct the fibration over the t-plane given by the level set of the function f. Since in this case, my function f is a quartic polynomial, the generic fiber consists of 4 different points that reduce to 3 when I approach one of the critical points. Now, taking trace of the coalescent point when I approach one of these critical points, I can construct the vanishing cycles, I can compute monodromies, use Picard-Lipschitz theorem to extract the intersection among the vanishing cycles, and use this intersection to construct my jump matrices that define my wall crossing structure. This is the procedure. Now, this second regime, delta smaller than 0, is similar to the previous one. Then let me skip it. Let me go directly to this last regime, which is the one in which something new happened. The situation here is depicted in these last two pictures. In this first picture, what happened is that 2 critical points go one into the other. Then I have a double root here. And what happened is that the corresponding thimble fuse one into the other, leaving a single thimble, which is this one. Okay, then this reduced the rank of my Betti homology from 3 to 2. In the last case, I have a triple root, then the corresponding thimbles fuse one into the other. I have a single thimble, that reduce the rank of my Betti homology from 3 to 1. The relevant point that I want to underline with this picture is that for different region in my parameter space, and in physics my parameter space corresponds to kinematic variable, to physical quantities. In case of Feynman integral masses, then spatial configuration of the masses and the external momenta, I can have a rank reduction. Then I need to study this. Now, let me go to the most interesting case, but even the most difficult, the case in which the function f is a multivalued function, which is the case of interest, for example, for Feynman integrals. In this case, the situation is more involved, and while the main construction underlying the analysis still work, we need some modification. To underline the main problem that can emerge in this case, let me look at the side of the pairing described by my Rham cohomology. And let me remind you that my cohomology group contain equivalence class of closed form with respect to this twisted differential. The point is that in the holomorphic case, this twist, alpha, is always a one form which is exact, given by df. In the multivalued case, this one form, it is closed, but it is not necessarily exact. It can take additional contribution. Then what I have to do, I have to study if I have this additional contribution. It is not something trivial. I have to check maybe case by case, okay? And to study this potentially additional contribution, I have to perform some geometric manipulation that are explained by Kontsevich and Soibelman in their paper. Let me summarize what I understood of the episode. Okay, the procedure consists in several steps. The first one is the one to choose a good compactification for my variety X, given in terms of three different kinds of divisors. I have this horizontal divisor, which is a locus at infinity, at which the closure of the function f has a finite limit. I have this vertical divisor, which is a locus at infinity, at which the closure of the function f has an infinite limit. And I have this log divisor, at which the f can have logarithmic. Now, let me explain what I mean with a good compactification. A good compactification has to satisfy these two properties. First, all these divisors be normal crossing, and only the divisor dv and dlog can have common irreducible components. Second, for any zeta in the closure of X, there exists a small neighbor of zeta in which the one form alpha can be locally expressed in terms of this alpha log plus alpha reg and alpha infinity, where alpha log can always be written in local coordinates near this divisor d log, parameterized by this condition, as a linear combination of d log forms, where the coefficients of this linear combination are periods of alpha around the divisor d log, essentially. Then I have a regular part that we are, I don't know, we are putting it equal to 0. I don't know if this is the correct thing, but okay, it can exist a regular form. Then alpha infinity, which can be written as an exact form, df, where this function f in local coordinates near the divisor dv, parameterized by this condition, can have pole of generic order. Okay? Once I have this good compactification, I have to study the behavior. I don't know why I have this thing. Okay. I have to study the behavior of the function of the closure of the function f along this divisor in order to understand which of these contributions really contribute to my one form that I need to define the twist. Okay, let me consider a concrete example. This example is motivated by Feynman integral in Bikov representation, in which the multivalued function is a logarithmic function. Again, Julio explained us that in certain theories, to loop appear elliptic curves. Then I'm choosing as argument of my logarithm that my Bikov polynomial is this elliptic curve. It is polynomial. Now, my variety x is given by C2 except this zero locus of the polynomial B. Notice that for different value of lambda, this is nothing else than the Legendre family of elliptic curves. Now, the compactification that I choose is simply this P2 that can be obtained adding to x the elliptic and this divisor at infinity, this P1 at infinity. Now, what we have to do is to study the closure of this form, or if you want, log of B. Okay, this is what we have to do. To understand which kind of this divisor are B equal to 0 and this P1. And we discover that the horizontal and the vertical divisor are empty in this case, and both of these divisors contribute to the logarithmic divisor. Then in this case, my alpha can be written just as a logarithmic form, d log of b. Okay. This is true in the regime in which lambda is in P1 except the values 0, 1, and infinity. And in this case, I can perform the description that I explained in the previous slide, construct my basis of thimbles, and construct my intersection among thimbles, etc. The procedure works, but since I have, I'm already over. No, I'm not over time. Okay. So, okay, but the most interesting thing appear the situation that we are not really able to solve. Okay, is the case in which lambda take one of these values, 0, 1, or infinity, and we cannot say, okay, we don't take this value because this is an equation of kinematics, this is physics. If we choose this configuration, we have this configuration. And we have to understand what happens when lambda takes one of these values. Okay, here the problem is that the elliptic becomes singular. So what we try to do is what happened in this case. We can use mixed asymptotic Hodge theory and study how the cohomology and the homology of this elliptic curve of this elliptic family change when we approach this point lambda equal to 0. And what happens is that the middle cohomology become empty, and the two form enhance to a the 2-1 form enhance to a 2 form and to a 0 form. This is what happened. This is just a description of my elliptic in the singular case lambda equal to 0. Okay, now if we continue using this twist alpha given by the d log of the Bikov polynomial, we obtain in this case with lambda equal to 0 a single non-degenerate critical point. This means one single thimble, then we have a rank reduction of the homology from 2 to 1, and no Stokes phenomena. Okay, this situation seems trivial. The problem is that the locus b equal to 0, when lambda is equal to 0, is a singular locus, this one in the picture. Then now, this one form alpha, given by the d log of p, is not globally well defined in its part. Okay, if you remember the problem when I have a multivalued function, we'll choose a compactification, then you can define a one form alpha, which you can define just locally, but you have to cover the whole space. Okay, in this case, this is not well defined in this point in which the elliptic becomes singular. We don't have a solution. Okay, that's our main problem. We try to do something. Okay, the first thing that we try to do is to do a blow up. Okay, then to choose new coordinates near to this locus. Okay, and to try to define one form locally close to this point. If we do this, and then we study the critical values, we notice that in this case, there are not additional critical values. But this is something that you can study case by case. I cannot claim that each time that I have a singular locus in my fiber, in my elliptic, in my K3, or whatever you want to take, I don't have additional critical points. It's something that, if this procedure is the correct one, I have to study case by case. I cannot claim something general. Okay. Another thing that we are trying to do, following a suggestion of Kontsevich, okay, is they want to approach parametrically this point lambda to 0. And what happened is that it seemed to happen that you have an accumulation of stock lines, okay, then a reduction of the homology, but due to the stock line, and not due to the fact that I don't have a critical point. Okay, maybe they are the same answer, and we see this reduction in this case as an accumulation of stock lines. This is possible, and this is the answer when we insist to stay in the point lambda equal to 0 and try to study the blow up, but it's something which we are working on. Then I don't have, it is something at which we are interested. I don't have a final answer to this. Okay, now let me underline some of the future direction at which we are interested. The first one, for a physical reason, we would like to test the analysis in Feynman integrals, because in this case I just choose an elliptic family, this Legendre family of elliptic curve, which is something very known in mathematics, just to try to do computation. But it would be nice to test the method in through Feynman integrals, and of course test the method in different representation, because if I obtain the same result for different representation, of course it's something physics, is a true property of the amplitudes. If this hold in a specific representation is something related to the representation that I'm choosing, then this is a big problem, I think. Then we want to study in detail this dependence of the pairing in the kinematic parameters, especially in the case in which the geometry in the fiber becomes singular. And we would like to perform explicit computation for Eiger-Calabi-Gauss. We do just elliptic curve. And we would like to try to use the method to analyze string question in string amplitudes. These are the main future direction. Now, before to conclude, let me bring to our attention this online workshop that we are organizing with Anthony and Matteo. It will be hosted by this Meetup platform. It will be between the 20 and the 22 of April. The registration will open soon in this website, and I invite all of you to register and to participate in the workshop. Okay, thank you.
Thank you, Roberta. Any questions, comments?
Yeah, so from the general setup, it looks as though there might be applicability to Fourier integrals, but there are issues with convergence and
No, sorry, can you repeat it?
I'm saying in the general setup, looks as though there could be applicability to Fourier integrals, but there are issues with convergence, behavior at infinity, things like that. Can you comment at all?
I cannot comment in this specific problem, but if the problem is the problem of convergence, this method is essentially a method to regularize integral. Maybe it can be applied, but I don't know exactly. I cannot comment really in detail because I don't know. I'm not so familiar.
I think the Fourier integrals is just like a case in the paper by Sigmund. Because you don't have this logarithmic exponent. So it's just
An holomorphic function.
Yeah.
Is a polynomial.
Yeah, and then
Well,
this
you,
would,
you still have a logarithmic exponent because you're ultimately doing things that you did right. But there still is a twist coming from.
there's a log omega. You mean?
Right.
Yeah.
But the issue is more is that behavior, or integrals and different behavior. So, as you're doing
Well, the thing here is then this would describe the analytic integration of the frequency. Gamma would be the frequency. And I guess if you're interested in asymptotic expansions, when the frequency becomes large in different directions, the complexity.
No, you're not.
You're not, but you're interested in analytic continuation, which maybe this tells you something about.
In the example that you mentioned, did you also study what happened at lambda equal to 1 or infinity? Is it always the generalized?
Now we check lambda equal to lambda equal to 1, and the situation is analogous to lambda equal to 0.
So just 1 point.
Yes, that's the main one of the main problems that we have.
And in the previous example, I think the one by Serge, you had configuration for which you have still 2 critical points or something. So it was dropping but not so degenerate.
In the pairs, you mean?
Maybe yes. And I was wondering whether if you know that configuration, you can do wall crossing. Yeah, in the middle one. You can do wall crossing, but to recover the 3, like in the opposite. Because it's degenerate, but maybe not too much. So maybe it's easy to compute because it's only 2. You only have to.
You mean that in this middle situation, doing wall crossing, I can recover the other. I don't know. Maybe I don't know.
So if I understand correctly, I mean, I thought there's 2 ways that this rank reduction can happen. One is that you find something that vanishes, which is these examples, this vanishing effect. But it could be also that there's some additional relation, that the geometry changes such that suddenly something becomes the boundary, which
yes, exactly.
do you have any example of that, or do you know if it kind of, because that's what seems that happens in the cohomology side. I would just find an additional relation that we didn't have, that tells you that something is exact. That
I think that I don't know, but maybe it's additional relation correct. But something is exact because you are thinking in terms of forms, no? I think that this additional relation appear in this case, no? Correspond to this case geometrically. No, to this case when you have we have multiple groups. This should, from the homology side, I think that should correspond to this. This is one method of reduction, and I think this would be maybe the one on this cohomology side. The other method of reduction is along Stokes lines, no? And maybe this corresponds to this exactly. Do you have other comments? Different comments?
No, we should check the cohomology side.
We should check the cohomology side. Like an intuition, maybe to this one.
I think in the elliptic curve, I think there's only one.
Yes, but in the elliptic curve, we didn't study this possibility, no? Because we have 2 critical points, and what we study is not the critical point that collage among them, is the problem, no? That one of the 2 disappear because it become an indeterminate form, no? It is not exactly this, no? Then I don't know in the elliptic.
Yeah, maybe it's if you have 2 functors and they
And
merge,
exactly, like this.
Yeah.
It should correspond to this, but in the elliptic, it's a bit different. Maybe I'm not sure. This.
slightly different direction. Can you say something? Did you find something new involving results about the solutions of basic analogy of these integral solutions on twisted cohomology and so on?
If I can find new solution in.
Or if you maybe can find new expression for these solutions or new information about it. Very simple technology of like twisted cocycles and
But they are twisted cocycle, no? Because I'm using a twisted Rham homology, no?
yeah. So
I'm using this. I think that, but yes, we have a different rank, because we are studying at the rank of the cohomology. If you mean this with a different number of solution, different cohomology class that stay in that for my cohomology group, this is what you mean, or not?
and let's think about some solutions of the KC equations, which are expressed as integrals of some exponential type function on twisted cycle, which look very similar to the type of functions we're looking at.
Okay.
And I was wondering if maybe in that case, the kind of technology you're looking at can give you additional information. I mean, this was honestly a bit vague question.
Okay, I don't know. I think that the geometric method. See, if you give me an integral which has an exponential form, give you all the possible integration contours, then all the possible solution in your case in which the integral converge. If they are more of what you already have, and I don't know that.
If no other question, let's thank Roberta. And let me thank also the other speakers and all of you for coming and attending this. And I hope to see you next week at IHS. Next Wednesday, there will be a talk in person. And you can check on the program online. Thank you.